Today in science, we are going to be looking at not just kind of the straightforward technology pieces of concepts, but also how they can be a little bit surprising. A magnet is something that can exert magnetic force. So this means it has the ability to attract certain magnetic metals, such as iron, steel, cobalt, and nickel. Fridges are usually made of steel, and so that's why when you put a magnet on your fridge door, it'll probably stay there, right? But magnets can attract or repel other magnets too, and that's because they have two opposite ends called poles, one north and one south. The underside of a fridge magnet is one pole and the top side is the other. Like electrical charges, opposite poles attract and like poles repel. If you put one fridge magnet on top of the other, they'll stick together, but if you try to push the undersides together, they'll push each other away. And I know in other grades you've probably experimented putting two magnets together and actually moving one across the table. So, what makes a magnet magnetic? Well, it has to do with the molecular magnets inside it. So when a piece of iron is unmagnetized, all of the little pieces point in different directions. But when it's magnetized, its molecular magnets are all pointing in the same direction. So that makes it clear, like everything pointing this way is south and everything pointing this way is north. These worksheets are in your Google assignment for yesterday, but feel free to pause the video and take a quick look at other parts of this page if you want to take a closer look. Now, as we keep looking at what we're learning about magnets, we might discover some surprises. So we'll start with some basics, like magnetic patterns. So there's a force field around every magnet called a magnetic field, where the magnetic force is strongest. The force created by the magnetic field makes invisible patterns called magnetic field lines. So that's what they've drawn here, is the invisible magnetic field lines. And these lines change when two magnets meet. So the lines around a simple bar magnet on its own look like this. So there's kind of a connection between the north and the south poles, but then as you get farther out, the north and south start to push away from each other. When two magnets repel, the lines look like this. So the south lines are all pointing towards each other and they actually try to push each other away. Whereas when the south and the north pole are connected, then the magnetic field lines actually connect to the other part of the magnet, and that's why they're attracted. Now, here is something interesting or surprising that you might not have realized. Magnetic migration. All sorts of creatures, from turtles to birds to butterflies, travel thousands of miles to find cool places in summer and warmer places in winter. Often they've never made the trip before, but they almost always end up in the right place. And that's because the Earth itself is a giant magnet. These animals can sense the Earth's magnetic field, which tells them if they're going the right direction. So this could be an example of an electromagnetism surprise. You might not have guessed before that electromagnetism or magnetism in general had anything to do with the migration of animals, but it does. There's also a little experiment that's often done in younger years where it's impossible to see the magnetic field itself, but you can use iron filings to see the pattern of the field lines. So if you have a bar magnet, some iron filings, and a piece of paper, and you lay the piece of paper on top of the magnet and sprinkle the iron filings on top, gently tap the piece of paper so the iron filings jump up and then fall down on the paper again. And what you'll see is that at the center here, they kind of make a band around, similar to what this looks like, and then at the end, they all spread out. So this pattern is quite similar to their drawing here, and that is what it's based off of. So to make a magnet, you can make all the molecules in iron or steel point the same way by stroking the metal repeatedly with another magnet. So if you were to take a needle that is made of iron or steel and you rub a magnet against it, you can actually polarize the needle, and then it will start to point one direction. We actually used to make compasses out of this. Oh, look, they have an example here where we would take a needle and we would magnetize it, and then we would lay it on a leaf in the water, and so it would actually turn to point north. You might also notice when you're at a restaurant that sometimes the cutlery sticks together. They will actually magnetize the cutlery so that it can stick to magnets in the rim of a bucket so that it doesn't get tossed out in the garbage. The biggest magnet on Earth is actually the Earth itself. It is one giant magnet. That's why we refer to the Earth having a north and a south pole. But we also talk about magnetic north pole and the magnetic south pole. Because the core, the very center of the Earth, is liquid iron, it acts like a bar magnet running through the planet. So the top end is the North Pole, and it's very near to what we refer to as the geographic North Pole, but the magnetic North Pole and magnetic South Pole are actually a little bit different. So if you are using your compass and your needle points, it points to magnetic north, not geographic north, even though there's a little bit of a difference there. Our big idea for this unit is about electromagnetism, and so it's actually asking what's the relationship between electricity and magnetism, and that's why we're talking about this here. And why am I reading about magnets in the chapter about electricity? So electricity and magnetism are very closely linked. Electric current always creates a magnetic field around it. So when a current flows through a wire, the wire temporarily becomes a magnet, even if it isn't magnetic the rest of the time. So it's only when that wire is connected to the electrical current that it has a magnetic field. As soon as it's unconnected, the electric field is gone. The magnetic field, sorry. The greater the current, the stronger the magnetic field it creates, and this is called electromagnetism. Electromagnetism can create really strong temporary magnets called electromagnets, and these are made by wrapping a long coil of wire around an iron core and then passing a current through the wire. Magnets can cause a current to flow too. If you spin a magnet around inside a coil of wire, voltage builds up in the wire. If the wire is connected to a circuit, the current will flow around it. The stronger the field and the faster the movement, the more voltage is produced. Inside a power station, water is boiled into steam, and then steam turns a machine called a turbine, which in turn spins a magnet around inside a coil of wire, generating an electric current that can be sent to people's homes. So this is what makes an electricity generator work. It's actually electromagnetism that is happening here. So you can make your own electromagnet using some insulated copper wire, a battery, and an iron nail, and some paper clips. So this is what they were showing in the Bill Nye the Science Guy clip that was on yesterday's assignment. So when the wire around the nail, keeping the coil very close, and wind the ends of the wire around the battery terminal, when you hold the nail near the paper clips, if it's connected to that current, it will actually magnetically pick up those paper clips. But if you have the wire not connected to the battery and there's no current through it, you won't be able to use it as a magnet. Now, here's another example of surprising electromagnetism. Hovering trains. So some countries, including Japan and the US, have really fast trains called maglev trains. These trains have electromagnets underneath them, and they run on tracks made of electromagnets. The magnets repel each other, so the trains never actually touch the tracks, and there's no friction between the train and the track, which makes maglev trains really speedy and efficient. So electromagnetism is actually how these hovering trains are able to work. So I wanted to start this lesson by giving you a quick review of electricity, magnetism, and electromagnetism. And yesterday you were learning, kind of searching for your own facts about these three vocabulary terms. Today I want to focus more on what are some surprising things we could learn about electromagnetism. So in our books, we had the surprise of migration, right? That migration is kind of impacted by electromagnetism. We also had the hovering trains, known as maglevs, that they're actually running on magnets. Your assignment today is going to be to do some research and to find your own electromagnetic surprise. So you will be kind of submitting this by commenting with the link on the Google Classroom assignment. So I will give an example as soon as I have uploaded the assignment on Friday, but I'm going to show you a couple of my examples here. Now, because we're in a Catholic school, we are asked to find kind of Catholic worldview connections to what we're teaching. So when I was looking up random things, I was looking up kind of like, are there Catholic scientists that study electromagnetism? Are there like, what's kind of the dealio? So you actually can find some interesting things. Like I found this article entitled, "I Was Attracted to Faith by Magnets." And so it actually tells the story of this kid. His dad was a Presbyterian pastor or elder, and he's also like a scientist. And so he discovered through an experiment with his dad, when he saw the filings of the iron, it actually attracted him to faith. And as he went further into discovering this, he found a lot of parallels between kind of a magnetic field and God, and like how you described them and different things that way. So it was an interesting perspective. So if I were to use this article to make the link, I would need to copy the link from the address bar. So you copy it and then just paste it into the comment. And also just write a little bit about it, but you'll see my example. The second article that I found, I actually found a different article, but this was one of the sources for it, so I went to the original, was that apparently there were some electromagnetic mysteries surrounding the opening of Jesus's tomb. So the tomb hadn't been opened for a few years, and when it was open, there were two things that they talked about. One was they talked about there being some like sweet scent, but the other one was that there was actually electromagnetic disturbances that were affecting their field equipment, and so they had a hard time with it. So when I'm showing you these articles, I'm not necessarily saying that everything is proven in fact, but there's some interesting like surprises or mysteries. I would not have connected the tomb of Jesus with electromagnetic disturbances and fields and forces. So once again, if when you're using your article, you're going to copy everything from the address bar and then paste it into the comment to use as the link. When you are posting your link, please make sure that you are doing this in the class comments. So when you open the assignment at the bottom, there should be an option for a class comment. If you put it in the private comments, it will only go to me instead of going to the rest of your classmates. So under the class comment, you are going to write a little kind of summary. So I might write something as simple as electromagnetic disturbances when they opened Jesus's tomb. And then I would just paste the link in, and when you submit the comment, it will make your link blue and actually a hyperlink that we can click to go and explore that topic ourselves. I really encourage you to go and look at what everybody else is kind of discovering as their surprises to see if there's maybe something that you find intriguing or surprising that you hadn't thought about before. As always, please be careful with anything that you are searching or posting, and make sure that like you've read the article and you know that everything in it is appropriate before you're sharing it with everyone.